welcome. This is the first talk, and I thought I would give an overview, necessarily brief overview, of the results of the AtLAST design study, the EU-funded AtLAST design study that I was coordinating. So first, I want to start with a brief scientific motivation for AtLAST. AtLAST stands for the Atacama Large Aperture Submillimeter Telescope. And the goal of the AtLAST project is to plan for this new astronomical facility. But why? So our understanding of the universe so far has been mainly based on observations in the optical and near-infrared wavelengths. And although there is, such as the image that you see here in the background, and although there is certainly still a lot to learn from this wavelength range, if we only use this type of observations, we are necessarily gonna gather a very biased and incomplete view of the universe. Indeed, to understand properly the astrophysical processes, we need to have a multi-wavelength view of the universe. And here I show the whole spectrum from the high frequencies, which carry the highest energy in the gamma rays, down to the longer wavelength, the lowest frequencies in the radio wavelengths. And astrophysical sources send us signal across the whole wavelength range that is shown here. Of course, from ground, we cannot observe every wavelength, but in some windows are completely blocked by the Earth atmosphere, for example, the X-rays, the UV, and the far infrared. The sub-millimeter window, I refer to it as the range between 300 micron and 10 millimeters. If you want, it overlaps a little bit with the microwaves, which are a longer wavelength. And in the case of the sub-millimeter range, we can observe it from ground, but there are some challenges that I will cover later. So there are some millimeter observations serve all fields of astrophysics, but probably the most immediate science goal is that these wavelengths allow us to study the cold gas and dust in the universe, specifically in galaxies. This slide shows the same patch of the Milky Way plane, our own galaxy. In the top panel, you see the image in the near-infrared band, and in the bottom panel, you see the same region in the sub-millimeter band. And as you can see, there are many dark patches in the near-infrared band, which are very bright in the sub-millimeter. And this is because the same gas and dust that are absorbed in the optical UV and the near-infrared wavelengths re-emit this energy in the sub-millimeter. So the sub-millimeter allows us to study these gas-rich regions of galaxies, which are also the most active in terms of star formation. And about 50% of the radiation from galaxies is observable in the sub-millimeter range. As I mentioned, the sub-millimeter wavelengths can be observed from ground, but it is complicated. And this is because the lowest layer of our atmosphere, the troposphere, contains many molecules, including water vapor. And these molecules have transitions precisely in the sub-millimeter range, meaning that they absorb the radiation coming from the sky, from astrophysical sources, before it can reach our telescopes. The only way to overcome this complication is to place our sub-millimeter telescopes in a very high and dry site. This plot shows the transmission of radiation. So when the fraction is 100, it means that all of the radiation reaches our telescope, so it's good, as a function of the frequency observed in the sub-millimeter range. And this plot shows the 25% best weather conditions in one of the best places for sub-millimeter observation. As you can see, in the lower frequency range, we are close to 100% transmission, so it's okay, it's relatively easy to observe this wavelength from this place, but above 400, 500 gigahertz, in the best case scenario, we have a transmission of about 50%, and in some some wavelengths, some frequencies are still completely blocked. And this is the best case scenario. This is the transmission in one of the best places on Earth. So you can see how complicated it is to observe these wavelengths. And the plot that I showed earlier was reflecting the transmission from the Chinatown Plateau in the northern Chilean Atacama Desert, which indeed is this huge flat land at a very high altitude, 5,000 meters above sea level. And it's extremely dry, so it allows some millimeter observations all year long, almost all year long, 11 months per year. And it already hosts the best sub-millimeter observatories in the world, ALMA, which is shown in this nice picture, APEX, ASTE, and CCAT, which is coming now. So the question that many of you may have is, why do we need ATLAST if we already have ALMA, which is the most powerful sub-millimeter observatory on Earth? ALMA has the real strength of ALMA is angular resolution, meaning that ALMA can produce images which are extremely detailed and can resolve extremely small regions. And this slide shows showcases three of the best, the most groundbreaking results from ALMA. The imaging of a protoplanetary disk on the left, in the center the shells around the dying star, and in the right the molecular gas in the spiral arms of a nearby galaxy. However, this angular resolution comes at a price. Indeed, ALMA is great at resolving small details, but it cannot capture larger scales, and it cannot efficiently map large sources, and even worse, it cannot measure the total flux of extended sources. Now, this is a little bit complicated to explain, so I tried to make an example in this slide. This that you see in the middle is the image taken by Herschel at 100 micron of the Small Magellanic Cloud, which is a small galaxy satellite of the Milky Way. And the resolution of this image is 7 arcseconds. Now, if we were to observe this object with ALMA, let's assume a wavelength of 870 micron, which is intermediate for ALMA, it's band 7, and let's assume an intermediate array configuration. The field of view of ALMA will be this very small dot that you see here, this Chan dot, which I zoom in here. It's 18 arcsecond field of view. But not only that, but ALMA would be only, not because it's ALMA, but any interferometer can only observe scales comprised between the angular resolution, which is this very small red dot here, and the so-called maximum recoverable scale, which is this bigger dot here. The angular resolution is the wavelength divided by the maximum distance between two antennas in the array, and the bigger circle is the wavelength divided by the smallest distance between two antennas. So ALMA can observe only scales between these two regions, but as you can see, there is absolutely no overlap with what Herschel can observe, because the Herschel image is so pixelated at in this very zoomed region. So the problem is that we have ALMA, which is extremely good at the details. We have previous single dishes and Herschel that provided these images, which have the whole, can map a large region, but with an angular resolution of a few arcseconds, but we have no way to bridge between these two. So ATLAST will fill this gap and other gaps. It will fill this gap in angular scales. It will fill a gap in sensitivity. It would be able, thanks to the large aperture, to discover new faint sources. It would fill a gap in sub-millimeter capabilities. Remember how difficult it was to observe a sub-millimeter. You need to have an extremely dry site. And what we have right now is these very large single dish telescopes that are shown in the bottom right, which have the large aperture, but they cannot observe below 1 millimeter very easily, because either because of the site or because of their design. Then we have the small aperture telescopes, which can observe in the sub-millimeter, but they don't have angular resolution. And we have ALMA. So AtLAST would bridge between these facilities. And another thing that I want to stress is that AtLAST can also improve the scientific output of ALMA itself, because it can provide ALMA with new faint targets that can be followed up with ALMA. The data from AtLAST can be combined with the data from ALMA to recover the missing flux that ALMA cannot observe. And AtLAST can also participate in long baseline interferometric campaigns, so enhancing the sensitivity of this experiment, such as the Event Horizon Telescope.
So 5 more minutes.
Okay, thanks, Aki. So in the next 5 minutes, I have to run through all the results of the AtLAST design study, which was concluded a few months ago. The design study was the work was divided in 6 work packages that the leaders are shown in these pictures. And we worked together with a team of about 80 people from the consortium, plus more than 100 external collaborators that helped us in this. So I start from the last work package because AtLAST is the specifications of the AtLAST telescope are driven by science, by transformational science goals. Work package 6 has produced 8 white papers, which are listed up here, plus several other peer-reviewed papers and an overview document, which is published in our website and on the archive. So it's very difficult to summarize 8 white papers, but we try to do this by showcasing these 3 big questions that AtLAST will address. The first one is, where are all the baryons? So AtLAST will be exceptionally good at measuring the total gas and dust content in the universe, thanks to this large field of view, high sensitivity, and also thanks to the combination of the two that managed to beat the confusion noise and so detect much fainter sources than previous surveys, down to the typical populations at any redshift. Then in the center, what we wanted to illustrate is the capability of AtLAST to detect not only the point sources, the compact sources, but also the filamentary environment in which they live. So the gas flows around the compact sources. And here I refer both to galactic and extragalactic sources. So the baryon cycle, the life cycle of gas and dust, and AtLAST will be able to do this thanks to this exceptional sensitivity to large scale emission. And finally, the third question, it's kind of a new science case for AtLAST. It will be able to do time domain science in the sub-millimeter wavelengths. So it will be able to do high cadence and rapid observations and high time resolution solar observations. So from all of these science goals, we get the following requirements. The wavelength range needs to be the same as ALMA. The diameter of the primary mirror 50 meters, 6 instruments at least, so serving a broad community, and the fast scanning speed. Work package 2 delivered on these requirements and delivered a telescope design that satisfies all of these requirements. In the left, you see the optical design, which is a classical Ritchey-Crescent design with the 2 imaging mirror, M1 50-meter diameter and M2 12-meter diameter, and the third flat mirror, which is folding the beam into the instruments. And thanks to the short focal length between the 2 mirrors and the third tertiary mirror, we can achieve a large field of view of 1 to 2 degrees in diameter, despite the very large aperture of the telescope. We have 6 instruments. 4, with the ones shown in red, are co-rotating in elevation in the wheel of the rocking chair design. You see in the right the CAD model of the telescope. The wheel is co-rotating in elevation and hosts the 4 Cassegrain type instruments, and the 2 large instruments are on the elevation axis, and they're placed on the Najmit platform, so they do not co-rotate in elevation. And another feature that I want to highlight is the surface accuracy of the primary mirror, which can reach down to 20 micron RMS at night, which allows observation at very high frequencies. And on top of that, Work Package 2 delivers an additional feature of the design, which was not in the initial requirement, and it is an energy recovery system based on supercapacitors, which allows the telescope to recover up to 85% of the peak drive power of 1.7 megawatt, which is needed for the telescope for the motors to move. Then Work Package 3 had the crucial job of selecting the best site for AtLAST. There was initial criteria set out which are important for some millimeter observations, and according to these criteria, the Work Package 3 team pre-selected the 2 sites, both on the Chinandol Plateau. If you're familiar with the area, when you come from the Alma OSF, you come from the Alma Road, which is here, then you have Alma on the right, and on the left you see AtLAST Site 1, the one in the Alma ISO concession. Then you pass Apex, and then you turn on this road going towards Cerro Toco, towards Simon's Observatory, and then on the right you see the AtLAST Site 2, the second site, which is outside the ISO concession. And on the top here on the right, you also see the Tau telescope on top of the Cerro Chinandol. Now, on both of these sites, we built dedicated weather towers, which measured the wind speed and the wind gust at very high temporal resolution, extrapolating the wind speed to the height of the AtLAST telescope. And we compared the data from several seasons, and we concluded that although both sites are eligible, site 2, the one that I zoom in here, is preferable because of the lower wind speed and also the lower snow accumulation. Then we go to Work Package 4, operations. Everything that makes a telescope work, an observatory work, is operations. So operations start from the site preparation and last until the last data is taken and delivered to the PI. The team behind the operation study has decades-long experience with operating large astronomical facilities, ISO, ALMA, APEX, SRT. So they used this experience for the operation plan of AtLAST, but they also introduced a new innovative concept that will allow AtLAST to work better in a changing future, in a future where the conditions are changing. So at the basis of the operations plan, there are key concepts: 24 hours observing with dynamic scheduling, remote distributed operations. The science is at the basis of everything, so high standards for the quality of the data, a public data archive where the data become public after 1 year proprietary period, and monitoring of the telescope system for preventing maintenance, but also maximizing the use and the sharing of existing infrastructure to limit the environmental effect of the telescope. Work Package 5 is probably the most innovative aspect of the design study of AtLAST compared to the design studies of other astronomical facilities. So we had a whole team of experts dedicated to studying ways to make AtLAST completely sustainable and powered by renewable energy. The priorities of Work Package 5 were minimizing carbon emissions, but not only that, reducing the cost of powering the telescope and fostering good relations with the local communities, in particular San Pedro de Atacama. The issues that were identified by the Work Package 5 team, this is a team of experts that has never worked with astronomers before, they immediately identified 2 challenges. The first one is the high power demand of AtLAST with peak power demand of 3 megawatt and average of 1.3 megawatt. But on the other hand, AtLAST is located in one of the most solar irradiated sites on Earth. But the second challenge is that AtLAST needs reliable power 24/7. So this reliability of power we cannot afford for security reason, but also for the for safety reason, but also for the instrumentation. We cannot afford power outrage. This implies that there needs to be a backup always available even after snowstorms to power the telescope and the instruments. So after a long study, which has produced many papers, the conclusion is that the best trade-off seems to be an energy system that uses solar panels during the day, a hybrid storage, green hydrogen and batteries at night, and a small backup diesel solution, less than 10%. And this combination gives the most economical energy in 2030 projected, the reduction of CO2 emission by 95% compared to the diesel-only scenario, but also a reduced mineral resource depletion and water used, comparable to a scenario where we use 100% renewables. I think I'm out of time, so I will just go very fast on this and just say that we have also studied the governance and impact of the AtLAST facility, and we learned from all this study that the implications of the AtLAST venture go beyond astronomy. We can maybe discuss this in the discussion afterwards, but especially the renewable energy study, the sustainability study can have big impact on science as a whole and society. And what comes next? We have now concluded the design study, but we got a new EU-funded grant, which will bring us to 2028. With this new grant, which is also coordinated by me, but we are expanding the AtLAST consortium. We are really becoming a global effort. We have 20 partners from 3 continents. We are now 150 team members, and we are also officializing the collaboration with Japan to merge the LST and the AtLAST effort into a single effort. And I conclude here.